Recently, we've been taking a look at perturbation theory, and this is basically how we approach quantum mechanical systems that we can't really solve exactly. Basically, we have some Hamiltonian describing some system, and we try to write it in a way of some unperturbed Hamiltonian that we can solve exactly, and then some perturbation Hamiltonian that describes the difference between that unperturbed, exactly solvable Hamiltonian and the actual system we're trying to solve for. And typically, this is some small scale perturbation. What perturbation essentially does for us is we say that we can take the energy eigenvalues of the Hamiltonian we're trying to solve and write it in terms of sort of an expansion. We're going to have a zeroth or unperturbed energy eigenvalue plus some first order correction to that plus some second order correction to that and so on and so forth, expanding out as to however high of order we want for whatever accuracy we need. And likewise, the energy eigenstates can be written in terms of the same sort of thing, a zeroth order or unperturbed eigenstate plus a first order correction to that eigenstate plus a second order correction to that eigenstate, and so on and so forth. And this is essentially what we're trying to get with perturbation theory. And a few videos ago, what we did is we, basically plugged these equations into our eigenvalue equation and kept track of the orders, and we got different equations that we could solve to get sort of the trivial one is the zeroth order um, equation, which is essentially the energy eigenvalue equation for the unperturbed state. Um, right? So that one's pretty trivial. That's essentially what we already knew. The first order perturbation equation um, can be written as the unperturbed Hamiltonian minus the unperturbed energy eigen values acting on the first order corrections to the energy eigenstate. That will be equal to the first order corrections to the energy eigenvalue minus the perturbation matrix acting on the zeroth order energy eigenstates, right? So this is what we've been looking, first order non-degenerate perturbation theory. And when we solved all of this, we ended up getting the results that our first order corrections to our energy eigenvalues were just the diagonal matrix elements of that perturbation matrix, right? This is, in terms of the unperturbed bases. But basically, yeah, there's the diagonal elements of that perturbation matrix. And the first order correction to the energy eigenstates is was just written for m not equal to n as the off diagonal terms of that perturbation matrix that sort of connect the m and the nth state divided by the difference in energy between those n and nth eigenstates, unperturbed eigenstates. So these were sort of our two results from first order perturbation theory. What we're going to move to today is we're going to take a glance at second uh, order non-degenerate perturbation theory. And with second order perturbation theory, the equation we came to in sort of the first video we did on perturbation theory is that equation can be written as the unperturbed Hamiltonian minus the unperturbed energy eigenvalues acting on the second order corrections to the energy eigenstates. And that will be equal to the first order corrections to the energy to the energy eigenvalues minus that perturbation perturbation Hamiltonian acting on the first order corrections to the energy eigenstates plus the second order correction to the energy eigenvalue acting on that zeroth order um, energy eigenstate. So this is the equation we're going to look at today. We're going to attack it, and we're going to end up looking for those second order corrections. Turns out those are the only things we don't know in this equation, right? Are the second order corrections to the states and the energy eigenfunctions. Yeah, presumably we did first order before we did second order, so we already know these terms of that of our expansion. The zeroth order states are kind of the exactly solvable ones we know. And we know the perturbation Hamiltonian because we know the system we're trying to describe here. So all we are really trying to solve for is those second order um, corrections. We're going to do the same sort of thing we did with first order, right? Where we're going to look at this. We're going to consider this in the matrix form, in matrix notation. I think is the clearest way to see it. And if you recall, we can write our vectors in terms of this. The unperturbed bases is just going to be a column vector of those coefficients. Oops, the first order corrections to the nth state, like this, that we calculated when we did first order perturbation theory. The zeroth order ones, obviously, since we're writing it in that zeroth order basis, it's kind of hard to see for a general state here, but these are just unit vectors. So if I take, say, the second energy eigenstate to zeroth order, it is just going to be a unit vector with a 1 in the second row of that column vector. What we're going to do is look at these sort of matrices, the matrix form of these things, of the left and the right hand side. This H naught minus En to the 0 in matrix notation, this unperturbed Hamiltonian, you can think about the matrix elements of this are just going to be those elements, right? You write the mth and nth row and column. So we cannot, this unperturbed Hamiltonian can act on this bra, and in matrix notation, this H naught minus En to the 0 term can be written as basically differences in energies along the diagonal, right? We end up with E. Let's look at for the n equals 3 state like we did previously. This is going to be E1 and 0 minus E3, the zeroth order state, 0, 0, 0, dot, dot, dot. In the second row, we're going to have 0, E2 to the 0 minus E3, zeroth order state, 0, 0. Third row, this is actually, sorry, once again, going to be 0 for the nth row. In this case, the n equals 3 row. And then the fourth row, again, would just be E4, 0 minus E3, 0, 0, dot, 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 and so on and so forth. So the left-hand side of this sort of equation looks like that, and it's going to be operating on this second order correction to the column, to our eigenvector, which is, C31, second order, C32, second order, C33, and so on and so forth, that column vector there. So this is the left-hand side of our perturbation equation over here, written in matrix notation. Multiplying it all out, the left-hand side is equal to just E10 minus E30 times C312. You end up with just a column vector that looks like this. 0 there, E40, C3, 0th order corrections, C3, 4, dot, 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 all the way down like that. And that's what the left-hand side of that perturbation equation looks like. The right-hand side has two terms in it, right? The first term here, and then the second one. The first term, that En, the first order correction to our energy eigenvalue, minus the perturbation Hamiltonian, acting on our first order correction to our eigenstate. Again, if we look at this n equals 3 state, this Hamiltonian, we're just going to essentially get our perturbation matrix with the energy. This term is just going to be along the diagonal. So in matrix notation, this ends up being E3 to the 1 minus the perturbation, the first diagonal element of that perturbation matrix, then minus H12 minus H13 minus H14, and so on and so forth. H21, E3 to the first order minus H22. And you see the pattern here. That's that operator in matrix form, and we're acting on the first order eigen corrections to our eigenstate. So this is just that column vector that we solved for when we did our perturbation, our first order perturbation. Now, one of the things we have to remember when we did first order perturbation is that this term is actually equal to 0, right? The first order corrections were perpendicular to the unperturbed states, which means that n equals 3 element of that first order correction is going to be 0, right? So when we multiply this whole thing out to get, this matrix operating on that column vector is going to give us a column vector. This whole thing, when we take it out and put it in a matrix form, is just going to be E3, 1 prime, C3, 1 first order. The next term is just H12 prime, C3, 2 prime. This third term, because again, this term, that third element is 0, is just 0. And then we have negative H14 prime, C3, 4, first order, dot, dot, dot. And, then we can, hopefully, you can quickly sort of see the pattern we're getting here. V3, 1 minus H2, 2, C3, 2. And again, 0 here, H2, 4 prime, C3, 4, dot, dot, dot. And we keep going through, but hopefully you get this column vector, right? That minus that, plus 0, minus that, so on and so forth, down this whole thing. This gives us our column vector. The one that is going to be important to us is we're going to focus on the nth row of this column. So I'm going to write it in a different color, but we have H3, 1 prime, C3, 1 first order correction, minus H3, 2 prime, C3 2 correction, plus 0 minus H3 4 prime, C3 4 the first order correction plus dot dot dot. And then this goes all the way down for however n dimensions our system has. So this is what this first term on the right hand side gives us as a column vector. The last term on the right hand side was just this, which is pretty straightforward to figure out. It's the it's the second order correction to our energy eigenstate acting on our 0th order times our 0th order eigenstate. Since this 0th order eigenstate is just a unit vector, this is essentially the unit vector 0 0 for the n equals 3 state again. This is just e n to the 2 where n equals 3. So that's the column vector for that second term on the right hand side. Putting it all together, we have our first order or our second order perturbation equation is that unperturbed Hamiltonian minus those unperturbed energy eigenvalues acting on our second order corrections to our energy eigenstates is equal to the first order correction to our energy eigenvalues minus that perturbation matrix operating on that first order correction to our energy eigenstates plus the second order correction to our energy eigenvalues operating on or multiplied by our 0th order correction. And in matrix notation, this is equal to, this is going to be probably tedious to watch me write out, but what we've just shown is if we look at that n equals 3 case, this whole matrix equation can be written as like this. And I don't know, maybe I'll speed this up in post somehow. So that's what it looks like in matrix notation. Looks like a bit of a beast, but if we focus on the nth row, that n equals 3 row right here, we have 0 is equal to this term here and that term there. Which means just looking at that row, if we, bring everything in here over to one side and leave d to the other, we can kind of quickly solve for that second order correction to our energy eigenvalue. And it's just going to be equal to H31 prime C31 first order correction, H32 prime, the first order correction, and so on and so forth. Like that. Or if we want to write this compactly, it is just the sum of the m not equal to 3, because we're looking at the n equals 3 state, element of the Hamiltonian times C3m first order correction there. And we've sort of sorted out what the second order energy correction to that energy eigenstate is. Since we've done our first order perturbation theory beforehand, we actually know what these C's are. Sorry. We know what these C's are, right? We recall from first order perturbation, this 3m to the 1 term is simply HM3, that off diagonal matrix element. divided by, well, this should be 3. We're doing the n equals 3 state. Um, it's this. This is what we have from our first order perturbation theory. So we can actually take that and sub it in, and in which case our second order corrections to that first order, our second order correction to our energy eigenvalues for that n equal 3 state is going to be sum over m not equal to 3 times h3m prime times hm3 prime over e3 0 minus em to the 0, right? These two terms, right, these, in Dirac notation are just going to be 3, 0. They're the matrix elements of that Hamiltonian, of that perturbation Hamiltonian, which, if we write it this way, hopefully it becomes obvious. This is just going to be the magnitude of that matrix element all squared, right? So it looks like that. So what we've got here written in a nice, geez, first day with the new pen. The second order correction to that n equals 3 energy eigenvalue is going to be the sum over m not equal to 3 of that matrix element of the perturbation Hamiltonian, magnitude of that squared, divided by the difference in energy level, unperturbed energy eigenvalues of the m and the n states. If we now, instead of looking at specifically n equals 3, we can write this sort of for the general n state. The second order correction is equal to the sum for m not equal to n of the matrix element of the perturbation Hamiltonian squared divided by the energy difference between the unperturbed states that matrix element is sort of connecting or coupling. And that's that. That's our second order correction to the energy of our perturbed system. The fact that the denominator is an energy difference between states means that the states that are closer together in energy are going to have, those matrix elements are going to have a larger sort of impact on the correction. The sign, whether that energy is going to be going up or down, is based on the difference of those. If we have, if this perturbation Hamiltonian sort of couples a higher energy state to the state we're looking at, it's going to actually lower the energy of that state, and vice versa. So the higher energy states coupling to that push the energy down, and the lower energy states coupling to the eigenstate we're looking at push it up. So recapping all of this second order perturbation stuff we've gone through, and we can just really quick run through it in Dirac notation. We have our second order perturbation equation that we derived a long time ago, a couple of videos ago, of this, where we have that unperturbed Hamiltonian minus the first order energy eigenvalues acting on the second order corrections to the energy eigenstate is equal to the first order corrections to the energy eigenvalue minus the perturbation Hamiltonian acting on the first order corrections to our energy eigenstate plus the second order energy corrections to our energy eigenvalue operating or multiplied by our unperturbed energy eigen states. Now, if we want to then look at this and look at the nth component, right? And just take that nth component of this whole thing on both sides and operate on that, we get this equation becomes this h naught n naught minus en the 0 and 0. Oops. This is the second order state there. We get that equal to n 0 and 1 times en 1 minus n 0 prime n 1 plus en 2 n 0 n 0, right? This Hamiltonian, this first term, this Hamiltonian can act on this bra, giving us en 0 times n 0 n 2, which is the exact same thing as this term. So this left-hand side of our equation is equal to 0. We saw that when we went through the matrix notation thing above. On the right-hand side here, this term right here is just that C33 first order correction there times En1. But we know that term is 0, right? That's the, we saw that the first order corrections to our energy eigenstates are perpendicular to the unperturbed state. And essentially that meant this term was 0. So that is also 0. And the only terms that are non-zero in this equation now are n0, those this term plus the second order correction to the energy, because this is just a Dirac delta function. So we have our second order corrections to our energy eigenvalue are n h prime rather, operating on that first order correction to our energy eigenstate. We know that from first order perturbation theory that first order correction to our energy eigenstate can be written as a sum Cmn 1 m not equal to n of those unperturbed eigenstates, right? So we can plug that into there, and this correction becomes n0 h prime. We can bring the sum over m not equal to n out here. C m n 1 m on 0, or written another way, sum over m not equal to n, C m n 1, those matrix elements of our perturbation Hamiltonian. We also know that those, from first order perturbation theory, that those coefficients are just those, go as those diagonal elements of that perturbation Hamiltonian as well, right? Divided by the energy difference between those two unperturbed energy eigenvalues. If we take that and plug it in there, we end up with the exact same equation we got above, just a lot quicker, but a little, a lot of the details of why these things, how we got there, a little more hidden, I think, in the Dirac notation versus the matrix approach above. But we get the same equation. And we see written more compactly, that the second order corrections to the energy eigen values are just the sum of the matrix elements connecting the matrix elements of the perturbation Hamiltonian connecting the n and the mth states squared divided by the energy difference of those states, those when they're unperturbed. And that is the second order energy correction from non-degenerate perturbation theory. Things you can notice is, the sign, whether this energy correction, whether that energy level is going to be shifted up or down by that perturbation, has to do with the difference in energies of the two states you're talking about. So if we have this perturbation Hamiltonian coupling the m and the n states, well, if the m state is higher than the energy, than the unperturbed energy of the state you're looking at, it's going to be negative and it's going to push that energy down. Whereas if that perturbation Hamiltonian couples a lower energy state to the eigenstate you're looking at, it's going to push that energy up. We also sort of see a bit of a problem that might come up here, in both first order perturbation theory here and in our second order results here. We have this energy difference in the denominator, right? And you can see why this is for non-degenerate perturbation theory, because if we have degenerate energy levels, those two energies are going to be the same. That's going to go to zero. This is going to blow up. We're going to have a different strategy to sort of approach perturbations on systems that have degenerate energy levels. That's what we're going to cover in the next video. In this video, we went through the second order correction to the energy eigenstate, eigenvalue rather, that came from looking at, if we go back to our matrix thing, we looked at the nth row of this, of our matrix form of our perturbation equation, and that solved our energies. If we want to get the corrections to our second order corrections to our energy eigenstates, we would just have to look at all the other rows and solve that. We're not going to really go through that in detail in any of these videos. We might discuss it a bit in the synchronous sessions, or over some homework assignments. What we're going to jump to now is this degenerate perturbation theory, how we can deal with perturbations on systems that have degenerate energy states, energy eigenstates. Hopefully you're following along with this. It's starting to make sense. If you have questions, email me, bring them up in the synchronous sessions, and we'll hopefully get through it. I will see you then.